Marine Communities Part 1. Topic 1. Marine Communities Background. Communities consist of interacting producers, consumers, and decomposers. So let's look at some of these terms first. Organisms are distributed throughout the marine environment in specific groups. These groups are called communities. A community is composed of many populations of organisms that interact at a particular location. A population is a group of organisms of the same species occupying a specific area. The habitat is the physical location, and niche comes from nidus, nest, is the occupation within the habitat, like the relationship to food or enemies. This is basically what is the organism doing. And then biodiversity is a variety of species in a given area. Communities with high biodiversities, for example, would be a coral reef. They are characterized by complex interactions between and among residents. Physical and biological factors affect communities. Some examples for physical factors are temperature, salinity, pressure, and the force exerted by waves or currents. Some examples for biological environmental factors are crowding, predation, grazing, shading from light, and competition. This diagram provides an idealized look at the tolerance of organisms to varying physical factors. And the example given here is temperature. To the left, you see low temperature. To the right, you see high temperature. And you can see this bell curve, and shaded in the middle is this optimal range. So when an organism's optimal temperature range is wide, as represented in this broad curve, it can survive wide swings of warm to cold temperature. If the curve were narrow, that would be represented by a steeper, tighter curve. Any small temperature deviation might be harmful or even lethal. The same reasoning applies to salinity tolerances or to pressure tolerances. Growth rate and carrying capacity are limited by environmental resistance. So here we're seeing the J curve. So these are organisms newly introduced into a favorable environment with no competitors for food or space, will reproduce exponentially, tracing a J-shaped population growth curve. In nature, very few populations reproduce at this maximal rate, however, because environmental conditions are rarely ideal, and because limiting factors in the environment quickly slow the rate of the population growth. And you can see in this diagram, the darker shaded area shows the J curve. The J curve is the steeper one of the curves. So this graph highlights the S curve, the other line to the right of the J curve. So environmental resistance causes the actual population growth curve to be lower than the maximum potential growth curve. So this figure shows the growth rate in number of individuals over time for both potential and actual situations. So when the limiting factors come into play, then a curve looking like this S-curve is being shaped. It gradually flattens towards an upper limit of the number of individuals in the population. The final number of organisms still oscillates around the carrying capacity, which is indicated in the horizontal gray line. The population size of each species that a community can support indefinitely under a stable set of environmental conditions is called the carrying capacity. So changes of environmental conditions change. Examples are if you are living in an upwelling area or in the upwelling seasons, or a predator is introduced, or the climate varies, or a new parasite is infiltrating the population. Population density and distribution. And the population density is defined as the number of individuals per unit area or volume. So in the top image to your left, you see random distribution. The position of one organism is in no way influenced by the position of other organisms in the same community. And this scenario in nature is very unlikely. In the middle one, you see a clumped distribution. That's a patchy aggregation of individuals. Conditions of growth optimal in small areas because physical protection, nutrient concentration, initial dispersion, social interaction. This distribution is the most common one in nature. On the lowest one is, of the images, the slides shows uniform distribution. This is equal space between individuals. You would have this scenario in an orchard where trees have been planted. And it's the rarest of all natural patterns. Marine communities change as time passes. So rapid changes, and I put 3 examples up there. One is a volcanic eruption. The other would be a spillage of sewage, and the other that could upset marine communities is putting in a dam. So climax communities are long established, stable communities, unless they are disrupted by severe external forces, including the ones I just mentioned, but also storms, disease, or any kind of pollutants. Disrupted climate communities can recover through succession, and succession are the orderly changes in species over time. Before we finish up the first topic, I have a couple of quick concept check questions for you. What is a population? Did you answer A? A group of organisms of the same species occupying a specific area. A population is a group of organisms of the same species occupying a specific area. The location of a community and the populations that comprise it depend on the physical and biological characteristics of that living space. So here's another quick concept check. The crazing of phytoplankton by copepod would be an example of plank influencing a community. If you answered D, biological factor, you answered the question correctly. Biological factors are influences on an organism by members of its own population or other population in its own or other communities. Biological factors include crowding, predation, grazing, parasitism, shading from light, generation of waste substances, and competition for limited oxygen. And this concludes our first topic of this chapter.